Today we're going to be looking at Ohm's law, which will help to tie together all the terms we've studied so far. So first of all, I want to make sure you understand what are the independent variables and what are the dependent variables. So we have control over the wire that we use in our light bulb or our speaker or in our motor. We control the resistance of the object that we're going to hook up. Okay, so the first independent variable is resistance. We know how to get the resistance using our formula. Okay, but the resistance is going to be treated as independent. We get to pick those things. The next thing we get to pick is the voltage of the battery. Based on the battery that we use in our circuit, we get to pick what that voltage will be. If we're not using a battery, I have a power pack here with a little knob where I can turn it and get different voltages. We are in control of voltage. We are in control of resistance. However, nature is in control of how much current will flow. We don't control that. So, once we hook up our circuit, a certain amount of current will flow through our wires and back into the battery. So we control resistance, we control voltage, nature controls current. How does it work? Well, with voltage, if we use a larger and larger battery, we will get more and more current flowing through our circuit. In fact, it turns out to be a direct relationship. It's proportional. If we have no voltage, we will have no current. If we double our voltage, we will double our current. It is a proportional relationship. The slope of this graph will be determined by the resistance. If I have two different slopes, the steeper slope is the one with less resistance. I will get more current for the same voltage. Okay, so this is our first relationship. It is proportional. Current is proportional to voltage. The next one is resistance. If I put more resistance in there, I have a wire with more resistance, I will get less current. Our graph for this one is going to be inverse. Notice I do not go through 0, 0. If I have zero resistance, I don't have zero current, I have infinite current. If there was no resistance, the current would be off the charts. There'd be nothing stopping the flow of electricity. Okay, so this is an inverse relationship with our normal inverse relationship equation. The Y is the current, the X is the resistance, and it turns out that the A, the graph constant, is the voltage of the battery. So this equation is the magic equation that relates current, voltage, and resistance. These two are the independent, the current is the dependent. Higher voltage, higher current. Higher resistance, lower current. So the equation one more time, I equals V over R. So I'd like you to try it. So we've got a voltage, we've got a resistance, and we're going to see if our current matches up. So we have brown, green, black. 15 ohms. We've got a voltage of 15 volts. And you'll notice we've got a current of 1 amp. So I equals V over R. 1 equals 15 over 15. And although this seems trivial because the voltage and the resistance were the same thing, I want you to realize that this is really the definition of resistance. It's the voltage needed to produce a current of 1. So when our current is 1, the voltage and the resistance are the same values. It comes from our new equation. So what I'd like you to find here is I would like you to find out all the things we can about this wire. So this wire is going to be used in a light bulb. And I want to know how bright is the light bulb going to be? How much current's going to flow through it? How much power is it going to have? How much energy are we going to use? How much is it going to cost us to run this thing? Is it going to blow a fuse? It all comes from these two simple things. So based on the wire's dimensions, we can find the resistance. We then hook it up to a battery with a certain voltage. And from those two things that we control, we can figure out current. Once we've got the current, we can find the power. Once we have the power, we can find out how much energy it's going to use in a given amount of time. We could then figure out how much that energy is going to cost. We could also use the current to see if we're going to blow a fuse. We could use the current to figure out how much charge comes out of our battery so we could see how long our battery is going to last before it dies. Everything comes from this equation. We control the resistance, we control the voltage, nature controls everything else, and we're smart enough that we can figure it out ahead of time. So give this a try and see if you can do it. We're going to make a bulb out of a material with a resistivity of 1.2864 e to the negative fifth. The wire is 75 centimeters long and the gauge is 34. So start with your formula and solve for the resistance of the wire. It's based on the properties of the wire that we picked. We're then going to hook this into a normal 120 volt American outlet. So find the current. Once you have the current, find out how many coulombs will flow through. We haven't used this one in a while, but its current equals charge over time. Take your current, put it in here. Take your 8 hours, put it in here. Solve for the charge. Find the power. 120 volts. We're in America. I, use whatever you got as your current. Energy. Power equals delta E over time. We're doing it for 8 hours. Find your delta E. How much is it going to cost? Once you have that energy in joules, turn it to kilowatt hours, turn it into cents. Then multiply by 365 because we want to do it for an entire year. In essence, we just did the whole unit in one problem. Everything is tied together. You start with the resistance, you use that to find the current, you use the current to find the charge, you find the current and the voltage to find your power to get your energy to get your cost. I hope this all made sense. If it didn't, come and see me during Macaulay 1 and I'll clarify whatever questions you might still have.